Attraction implies something else, so I hesitate to use that word, but in a sense, yeah.
What does the last one say? Positive charge goes.
Same direction of external electric field. What this allows us to do, the reason why this has any bearing whatsoever, is I don't need to know the source anymore. I could just say I have an electric field that's going to the right, and I stick an electron into it. Which way did the electron go? Electron will be attracted, will be going that way. It has no idea what's here. It doesn't, initially it doesn't know if it's going away from negative or towards positive or both. It just knows, oh, there's an electric field here. Now, it should be getting a stronger electric field if it's going towards positive, and a weaker electric field is going away from negative.
Are neutrons ever going to be introduced into those fields?
Neutron potentially can be polarized, but not particularly well, unless you've got really huge charges there. But a neutron, for the most part, is just going to ignore it.
Okay.
It's got a serious case of ennui. All right. Any questions right now? Because we've explained electrons repelling each other, or electrons attracted to a proton, or protons repelling each other, two different ways now. One in terms of opposite attract, like repels, and the second in terms of the electric field. Two more ways of doing this. And I know you're pumped to figure out what those are. Flashback, some good memories here. Conservative forces. What is a conservative force? Or why would a force be called conservative?
There's no outside. It equals beneficial minus one. It's a closed system.
No, it's independent of closed or open. That's a momentum thing. What's conserved?
It changes energy from one form to another.
Okay. Energy is conserved. It will just change it from one form to another. Kinetic, potential to kinetic. Electric forces are conservative forces. We now have gravitational, ideal elastic, and electric. We have three conservative forces now. So if I take an object here, some charge, whatever it happens to be, at rest. So it starts at rest. The initial speed is 0 meters per second, and then it starts to move. What can you tell me about the kinetic energy if it goes from rest to start to moving?
Kinetic energy is increasing.
Say it louder.
The kinetic energy is increasing.
Okay, and so what can you say about the potential energy?
It is decreasing.
Okay, so that's a key concept there. So if it goes from here to, and then starts to move, then moves, kinetic energy goes up, potential energy has to go down. Because the total has to stay the same. It's transferring energy from potential to kinetic. So whichever way this charge moves, it has to move to a lower potential energy. So I guess the question might be, what's potential energy in terms of electric? What is electric potential energy? It's a conservative force. There's got to be a potential energy formula. So potential energy, electric potential energy, It looks a lot like the force formula, except for the denominator. So we got this electrostatic constant, Q1, Q2 over R. The force is R squared, this is just R. It's not part of the derivation, but if a memory trick helps, remember that work, which is related to energy, is force times the distance. So if I take my force formula and multiply times the distance of R cancels out, and I'm left with this. So if I have a positive charge here and a positive charge here, will my potential energy be positive or negative? Do you need numbers? So positive, when we say 1 coulomb and 2 coulombs, and the distance between them is 3 meters.
Positive, right? Because. Positive. Both sides are positive.
Okay. K is a positive number. R is always a positive number. The only thing that could be negative are the charges, and I said they're both positive. All right, so let's not worry about those numbers. Let's assume that K times Q1 times Q2 is 5. So, for example. Now, if R gets bigger, what happens to my fraction?
It's small. Wait,
You're unclear?
It's small.
it's small.
Yeah, okay, so if R gets bigger, so as R goes up, then my potential energy goes down. Well, that seems to fit with what we were talking about over there. If I have two positive charges, I know that they will repel. As they get farther apart, the potential energy drops and the kinetic energy increases. Just as we would expect with a conservative force. Now, questions to hear before I make it seem more difficult? If I have a fraction, and b gets bigger, what happens to the fraction?
It's smaller.
Anyone want to counter that, or are you good with Marina's answer? Jonathan's got your back. You're good with it also?
Yeah.
All right.
Like, we have nothing.
Ready?
Oh, just, we have nothing else except that and the grows bigger, right?
Yes. Okay, feeling good? All right.
So far.
Then let's take a look at this over here. Oh, that's not what I wanted to do. Got lasso. All right, I got a negative charge and a positive charge. What's going to happen to them?
You're gonna come together.
Yeah, they'll be attracted. And so R is going to get smaller. If R is getting smaller, does that mean my potential energy is getting bigger? Got a yes over there. Which means if I'm gaining potential energy, I have to be losing kinetic energy. Which doesn't make any sense, because if it starts at rest and starts to move, my kinetic energy increases. How can I have both potential and kinetic increasing?
So the numerator of your fraction becomes a negative,
Okay,
which means that as r is decreasing, now your number is getting more negative, which means that it's decreasing.
so A over B, if B goes up, A over B goes down if
A is positive.
A and B are positive.
Oh, yeah, right.
Are the same sign. I guess I should just write it as if A over B is positive. If B goes up, A over B goes up if A over B is negative. Because it does become more negative. Put it down somewhere. So again, we're left with their opposite signs, they will attract, which means that R gets smaller, and because it's a negative number, it becomes less negative. The fraction becomes less negative, and therefore potential energy.
Fraction becomes more negative.
Oh, thank you. As R gets smaller, potential energy becomes more negative, which means we're losing potential energy, gaining kinetic, as we would expect. So we now have three ways of explaining the exact same thing. Questions here, because there is a fourth way. All right, then why don't we take a break here, come back, while you're all hyped up, come back, and we'll talk about that fourth way and start talking about some words that I know you've heard before when dealing with this, that you heard before this class even began.
Each other, or the electron gets sucked into proton and forms a neutral particle neutron.
Oh, okay.
So it turns out the answer is yes. The possibilities that you probably entertained.
I guess it just depends on the situation.
And the role of the die. All right, here we go. A fourth way of explaining the exact same thing.
Oh boy.
It's a deuterium nucleus or something?
Deuterium nucleus would be a hydrogen atom with a neutron in it, in the middle. Tritium got two neutrons in it. All right, so let's sort of recap what we have so far. If I have two particles, let's just say two charges, and I'm dealing with a vector, I got force. I can use force to describe it. The force of 1, 2 is K, Q1, Q2 over R squared. Formality. Throw in the vector stuff. The unit, what is the SI unit of force? Okay. If we're dealing with a scalar, and I got two charges involved here, I'm dealing with potential energy. So I have U sub E is equal to K sub E, Q1, Q2 over R. And what are the SI units of the potential energy?
Joules, but in this
Yes.
case,
Joule. If I had just one charge, you know, like the proton in the universe with nothing else around it, it's giving off these pheromones, this electric field. Well,
Wouldn't it be a lowercase q?
all right, so uppercase, lowercase q. The difference is textbooks tend to use lowercase q for a single charge, and then uppercase q for a collection of charges. So it's a 99% rule, it's not 100%, but 99% rule, the charge on that would be an uppercase q because I got a bunch of charges there, but an electron would typically be a lowercase q. As I've noticed, I will do uppercase, lowercase q almost interchangeably. Just whatever letter you're using for that particular charge, just stick with it. Ty?
Those are both Q, or lowercase k sub e, right?
Yes.
Okay.
Oh, yeah, I drew it abominably.
I couldn't see what was on the end of the bottom k.
Is there ever gonna be a point where the charges are interacting with heat, so how would we differentiate the different Qs?
Well, not in this course,
Okay.
definitely. You might run into that in solid state physics, which would be senior level physics majors.
Would it be Q subscript heat and
Alright, so have I run across that? You get into, because there's conductivity, there's thermal conductivity, and there's electric conductivity, which aren't the same. It's been too long. I can't remember how they dealt with it. We will not deal with that. I will not give you a heat and electric problem in the same, with the same stuff. Alright. So the electric field cannot depend upon the second charge. So basically you take the force and you remove a charge. So it's K E times Q over R squared, R hat. And that's the formula for an electric field. Basically it's that formula and you take out the other charge. R hat does change a little bit because this R hat is relative to whatever's creating the electric field. If Q is positive, then it's positive R hat direction, which means away. And if Q is negative, it becomes the negative R hat, which means toward. Thus, negative charges, the electric field comes towards it. Positive charges, it goes away. The SI unit. It's not a single word. You have to combine two units. Hint, look at what we did, go from here
stat
to here.
coulomb?
Say it again.
Stat coulomb?
Stat coulomb would be a unit of charge, not electric field. Stat coulomb is the CGS system, it's not international standard right now.
Does it have the word electric in it?
The unit?
Mm-hmm.
No. What is the difference between that formula and this formula?
The n squared, the two masses,
Say it again.
the two Q's.
All right, that has two Q's, this is only one. That's a hint towards the unit.
So it's Newton meters over C squared.
Over C squared? No. All right, so K is, so the unit, if we did the bit of the units, this is Newton's meter squared per coulomb squared times coulomb divided by meter squared. What are we left with?
Newtons per coulomb?
Yes. So basically you have your force and you just divide by the charge you don't care about. And so Newton's divided by that, the unit of that charge, Newton per coulomb. So this is what we've covered so far. Obviously the electric field equation I had written down before. But there's obviously a gap here. Something that requires only one charge, but it's a scalar, and the formula KEQ over R. Basically, you take your potential energy formula and you get rid of one of the charges. And so we would have units of this, well, it's a joule over there, and then we divide out a charge, so that's a joule per coulomb. Now, this joule per coulomb was too much for physicists to write, so they came up with their own unit, and it is the volt. This is not the formula for voltage. Just want to put that out there. It's related to voltage, but it is not the formula for voltage.
So it would go in the bracket.
All right, the symbol that is used for this is a capital V. This is capital V here stands for electric potential. At this point, if I am talking about potential energy, I need to use the word energy. Back in chapter 7, if I said, hey, what's the potential? It's the energy, what I'm talking about. Here, if I say, what's the potential? I'm talking about this one, the electric potential, not the electric potential energy. So again, if I want to deal with energy, I need to specify the word energy. So let's crank through a little bit of math here. I've got a 3 Coulomb charge, positive 3 Coulomb charge. If I am, well actually, why don't I make it nanocoulombs? 3 nanocoulomb charge. If I'm 1 meter away, what is my electric potential? And for the purists, assume
U sub E and V equals 0.
1 meter away, we plug into the formula over there. I know that the potential is KQ over R. That's 9 times 10 to the 9th, times 3 times 10 to the negative 9th, divided by 1. And so yes. I chose nanocoulomb so it can